Swayam Prabha. Digital India. Educated India.
I welcome you to this lecture of flow through porous media. What we were discussing in the last lecture was immiscible flow. When two phases they are immiscible, that means oil and water, and if we want to have flow of two immiscible phases through a porous medium, what all complications or what all physics evolves in that. So, in this context we are heading towards relative permeability and two phase flow, and then we will build on it and further we look into other aspects. What we discussed at the end of last class was that for a non-spherical cap, how this Laplace pressure was defined. So, we were building on that. We showed in the last class that if we pick up a region around point P, basically the distance of all these points of this line, they are same if we follow the surface. So, it is basically a surface we are talking about. This surface has multiple radii of curvature. You can see if I draw CD, it has the radius of curvature is R2. If I draw AB at the same point P, I have a radius of curvature R1. And in this case, we showed that for a sigma dl for dl element length on this curve, the surface tension force, that is sigma into delta L. For delta L length of this element, we have the force at sigma delta L. Now, what we need to do is we need to integrate this over this entire curve to get the net force by which this surface net force this surface is subjected to. So, what we found was the contribution from point A, point B, similar delta L element, similar delta L element point D, similar delta L element point C. So, all these 4 delta L elements, if we sum them up, we see the contribution of all points A, B, C, D as sigma delta L into 2 rho divided by capital R1 plus 2 rho divided by capital R2. R1 and R2 are the 2 radii of curvature, and then we said that because of Euler theorem, these 1 by capital R1 plus 1 by capital R2, that is equal to 1 by small r1 plus 1 by small r2, where R1 and R2, the small r1 and small r2 are the principal radii of curvature, Okay, so, this is so what are the principal radii of curvature? That is generally the maximum and the minimum. Because you can have multiple radii of curvature, out of those the minimum and the maximum, those two are represented by small r1 and small r2. So, what we did in that case is we said that now what we are putting here is that the forces due to surface tension is to be balanced by the pressure forces for mechanical equilibrium. That means, we are holding a curve like this. So, inside the pressure is P double prime, outside the pressure is P prime. So, difference between this P double prime and P prime, this difference in pressure, that would be equal to these difference in pressure will support, I mean otherwise the surface tension force will tend to reduce the volume of this sphere or volume of this region. So, now only force that is compensating, only force which is opposing it, countering it, is the in the mechanical equilibrium, that is this P double prime minus P prime, these two, the difference in these two pressures, that is countering the surface tension force. So, now if we go back to the if we go back to these our original one here, the area that we have, area over which this is, so this is the radius is rho. So, inside we assume that the pressure is say P double prime and outside the pressure is P prime. So, this difference in pressure multiplied by this area of this surface. So, that is basically pi rho square, rho is the radius of this curve. So, this is the curve is drawn such that every point on this curve is rho distance away from the point P, but you have to, for the rho is following the surface. Okay, rho is not just joining two points as a straight line, rho is one has to follow the surface and that distance is rho. So, now, so this is the area, and over this area the difference in this pressure P double prime and P prime, that is acting. So, what is the net force on this? So, net force is P double prime minus P prime into pi rho square, the pressure difference multiplied by the area over which this difference is acting, that is equal to, what they are doing is, here we are looking at 0 to 2 pi rho by 4. So, that means that the perimeter is given by 2 pi rho, that is the perimeter. This is the perimeter over which the force is acting. Here it is P double prime and here it is P prime. So, this perimeter is 2 pi rho. Now, since you are doing the you are accounting A, B, C and D, all four sides. So, that is why this integration is done over this length, the integration is done over 1/4 of the total perimeter, because you are already accounting these four forces. So, to avoid repetition of forces, integration was performed over 1/4 of the revolution, and so that is why the integration is between 0 to 2 pi rho by 4, only 1 quadrant, and so that is why it is. So, accordingly this comes here as sigma into 1 by r1 plus 1 by r2 into pi rho square. So, obviously this becomes, so one can write P double prime minus P prime, that is equal to 2 sigma divided by Rm. Rm is the new term we are coining here. Rm is the mean radius of curvature, where 1 by Rm is half of 1 by r1 plus 1 by r2. So, these are this is Rm is the mean radius of curvature. So, P double prime is the pressure on concave side, that means if the pressure on the concave side, that means this side the pressure is P double prime and the other side is P prime. So, that is the pressure difference. So, last time we had already seen that if we look at capillary rise, we saw that it is simply, if the capillary radius is r, it is 2 sigma by r. Now, for an arbitrary surface, it would be 2 sigma by r m, where r m is the mean radius of curvature. Mean radius of curvature means it is 1 by r m is half of 1 by r 1 and 1 by r 2. What are r 1 and r 2? These are principal radii of curvature at that particular point P. So, principal radii of curvature, that means the maximum radius of curvature and the minimum radius of curvature. So, this is what we learnt now. Further, we need some quick brushing up of our understanding of contact angle. This you have already studied before, but I just very quickly I would like to go through it. There is this famous Young's equation, which says that if there is a surface of a solid and a liquid is sitting there, then a force balance can be drawn to arrive at this expression. Okay. So, accordingly, if one has say for example, you remember when we looked at the capillary rise and this was the meniscus. So, the surface force was acting in this direction and we have drawn the component of it in vertical direction. So, these treatments we could do with this understanding. So, now measurement of contact angle, this contact angle can be measured by taking a photograph of the contact angle on a surface. For example, we can see here in this case the contact angle is less than 90 degree. So, this is considered more of wetting phase, whereas in this case the contact angle is the earlier case it was less than 90 degree, now it is more than 90 degree. So, this is considered as non-wetting phase. Okay. So, it depends on what is the substrate or what is the liquid we are looking at. So, now there are ways to measure this contact angle. One is by taking directly the photograph and doing the image analysis. There are other ways of doing it. For example, a solid plate can be placed inside a liquid and then can be gradually tilted. When it is seen that the plate has to be rotated, a plate has to be rotated until the liquid remains flat up to the face of the plate. So, liquid remains flat as long as this becomes a straight line, this liquid gets flat here. So, then it becomes if one makes it more vertical, then you find that there is a rise in liquid level. So, it is as long as this remains flat. So, that angle can be measured and this angle can be found out. So, this is referred as tilting plate method. Okay. In case of oil water system, since that is something which we have here in mind. I mean, when we have, for example, looking at a reservoir flow or two phases where oil water we are talking about, generally this oil water contact angle measurements, particularly for reservoir applications, for hydrocarbon recovery applications, there is a way to measure contact angle, which is where these flat polished crystals of the mineral that is predominant in the rock surfaces. So, one makes these crystals and this is the crystal, that is what you can see here. These crystals, they are these crystals are placed, they are immersed in something called a formation water. That means formation water means the water that is existing in a formation. Formation means hydrocarbon bearing formation. So, and then a drop of reservoir oil is placed between two crystals. So, you can see outside there is water and inside there is oil, and this is placed between two crystals. These crystals are flat polished crystals of the same mineral that is predominant in the rock surface. So, now a reservoir oil is placed between two crystals and then the plates were displaced relative to each other. That means, this plate remains fixed, this plate moves in this direction. So, this plate has moved. So, you can see this is the arrow. So, this plate has moved in this direction. So, now this is the shape of this droplet. So, from here one can measure the contact angle. Not only that, this is then referred as water advancing contact angle, because here in this case this plate is pulled. So, here water tends to advance, and what in this regard something which is very unique, which one must note here, is something called contact angle hysteresis, which can be shown here in this picture. When the fluid is introduced here, you can see the fluid is moving in this direction. So, this is the contact angle, whereas when fluid is drawn out from here, this becomes the contact angle, and you can see that this contact angle and this contact angle, they are different. Generally, this advancing angle, here it is the advancing angle, here it is the water advancing contact angle. Okay. So, because water is advancing. So, advancing angle is much greater than the receding angle. So, this is known as hysteresis. Okay, see that is how the that is how hysteresis is defined. So, contact angle depends on history of how contact angle is created. The reasons for this hysteresis are: number 1, contamination in liquid or surface of solid; number 2, there could be surface roughness; number 3, immobility at the surface in macromolecular scale due to adsorption or presence of surfactant. So, because of many reasons, there could be such thing happening. I mean, whether liquid is being pushed or liquid is being pulled, it depends on that, the contact angle can change. So, this aspect one must remember when we are going to now define the two phase flow. So, now we had talked about the sigma SL, sigma solid liquid, sigma liquid gas, sigma solid gas, and they have a balance here. Sigma Lg cos theta is equal to sigma Sg minus sigma Sl. Now, in the event sigma Sg is greater than sigma Sl plus sigma Lg, sigma Sg is greater than sigma Sl plus sigma Lg, sigma Sg is greater than sigma Sl plus sigma Lg. Sigma Lg means cos theta, this can have the maximum value of 1, and that will happen when theta is equal to 0. Okay, so, cos 0 is 1. So, sigma Lg plus sigma Sl is equal to sigma Sg. I mean, if we take sigma Sl from right to left, then you write sigma Sg is equal to sigma Lg into 1 plus sigma Sl. So, now here we are saying that when it is sigma Sg is not only equal, but greater than this. So, when sigma Sg is greater than sigma Sl plus sigma Lg, so naturally it is beyond cos theta is equal to 1. So, that is why it is written here that no theta satisfies Young's equation. So, essentially what this means is liquid will weight the solid perfectly. I mean, it is beyond theta is equal to 0 degree. Theta equal to 0 degree means it is completely weighting the surface. Theta greater than 90 degree means it is not weighting the surface, it is sitting on the surface as a blob. Okay. So, now, but theta is less than 0 degree means it is practically no theta satisfies Young's equation, and liquid will weight the solid perfectly. Under such situation, one defines a term called spreading coefficient SLS, which is equal to sigma Sg, how much it is greater. Sigma Sg is greater than sigma Sl plus sigma Lg, but how greater? So, that term one generally looks at spreading coefficient. Okay. So, this will definitely spread, there is no doubt about it, it is 100% weighting, but how strong would be this weighting tendency? So, SLS spreading coefficient is defined as sigma Sg minus sigma Lg minus sigma Sl. On the other hand, so this is the case when theta equal to 0 degree or even less, no theta can satisfy. On the other hand, when theta is greater than 90 degree, then we say that the liquid will not weight the solid, because if this is the solid and then if theta is equal to 90 degree means this is the angle and this is the angle it makes, which is greater than 90 degree. Theta is equal to less than 90 degree means, so theta is equal to less than 90 degree means, so this is the angle and this angle is less than 90 degree. So, it is weighting. This angle when it tends to 0, that means the film is almost spreading like as much as possible. So, now in this case there is some issue with this oil solid interface age. This is something which researchers have observed while working with a reservoir, in case of hydrocarbon reservoir. What they observed is that after the solid and oil they are in contact for ages, one can see that this weightability can also change. So, what they have observed is for when this oil solid interface age increases a lot, then at some point of time from 60 degree contact angle it can go beyond 90 degree. So, there could be a shift from little less than 90 degree to little above 90 degree. So, that is also not that is also something which is possible. Don't strike it off as something impossible. So, over age, if something is in contact, then there is a this equilibrium contact angle is so in this regard, I think one needs to look at this definition of equilibrium contact angle and how it is different from advancing and receding contact angle. But this equilibrium contact angle can shift from less than 90 degree to greater than 90 degree. Now, suppose we have a situation, we had already talked about a situation where we have a pore, cylindrical pore. Okay. So, when we have a cylindrical pore, at that time we have, let us say we have this is a cylindrical capillary. So, inside let us say we have water, which is the waiting phase. That means, the capillary is something similar to glass. So, it is water waiting. So, the substrate, the capillary wall is water waiting, and water is inside at, let us say, at a pressure of, let us say, 1 atmosphere pressure, and outside. So, it is filled with water, and outside let us say we have oil. I mean, water and oil, these are, I mean, we are talking about one is the waiting phase, another is a non-waiting phase. So, waiting phase is inside at pressure of 1 atmosphere, and outside it is all non-waiting phase. So, now we will have, in that case, there will be a meniscus developing, and this would be the meniscus, because one has a contact angle, and that contact angle, water will make a contact angle which is less than 90 degree. That is why you are calling it water wet. Had it been oil inside and water outside, this would have been a different curvature altogether. You must understand that. Had it been oil inside and water outside, then the curvature would have been different. So, now this is water and this is outside, it is oil. So, there is an angle, there is this angle here, which is the contact angle. So, this is how the surface tension would be acting. So, we have already talked about this in case of capillary rise. In case of capillary rise, gravity played some role. In this case, gravity does not matter, since it is horizontal. I mean, and the dimension of the capillary is small. So, gravity does not come into play. So, now we have, if r is the radius of the capillary, cylindrical capillary. So, in that case we know 2 pi r is the length of the perimeter of this cylinder, and inner perimeter, inner wall, and then that multiplied by sigma Newton per meter into meter, that gives me the force by which this surface tension is acting. Maybe you multiply it with cos theta to talk about this angle would be, if this angle is theta, then this angle would be theta, and then you can take the component in vertical direction, which is 2 pi r sigma cos theta. Okay. So, this is the force by which this is the surface tension force, and this surface tension force has to be compensated by what we have seen already, p double prime minus p prime is equal to, this is the force. So, p double prime minus p prime would be force divided by the area. That is exactly what we had done earlier in case of non-spherical cap, and earlier even for the spherical cap. So, this would be the area would be pi r square. So, p double prime minus p prime, or in other words we can think of p double prime. I mean, what we had done earlier was probably a little different. Earlier we had multiplied this pi r square to this side. So, that means we had multiplied this by pi r square. So, pi r square into p double prime minus p prime, that gives me the force, pressure difference for mechanical equilibrium, the pressure difference across this. Which side is p double prime? It is p double prime on this side. You remember, if just match it with what we had done earlier, and this is p prime. So, p double prime minus p prime over this area pi r square, that gives me the force, and that force is ensuring that this interface is not squeezing the liquid to 0 volume. So, then this force has to be compensated by pi r square. P double prime minus P prime. So, accordingly this P double prime minus P prime would come to 2 sigma cos theta divided by r. So, that is what, so this is what we referred as Laplace pressure in case of a sphere. This we are going to refer as capillary pressure. Our logic here is that oil will never enter into water phase unless you provide this difference. So, that means P prime is 1 atmosphere, outside oil is 1 atmosphere. So, let us say I have increased this pressure of oil by a little bit, nothing will happen, there will be no flow. Though I have a pressure gradient from this side to that side, there will be no flow. Unless the flow will only set in only when this pressure on the oil side is the pressure in water plus 2 sigma cos theta by r, then only there will be flow from this side to that side. So, I would expect the flow to take place from this way, the flow would take place only when the pressure on the oil side, is pressure on the water side, which we have probably assumed as 1 atmosphere plus 2 sigma cos theta divided by r. This 2 sigma cos theta divided by r, that is referred as the capillary pressure. So, one must, so if we have oil and water flowing simultaneously through this pore, one thing is for certain, that the oil pressure has to be higher than the water pressure, and how high, how much higher? By this amount, and that amount is known as capillary pressure. So, this is something which we must keep in mind now, from now on, that I am having oil and water flow, water is flowing in its own pressure, but oil has to be at a higher pressure, then only oil will get into this pore. Now, we will look at this definition of capillary pressure when the pore that we are talking about in porous medium, that may not have to be cylindrical, that may be conical, there may be undulations. So, how capillary pressure will be defined in those cases. So, that is something which we are going to take up in the next lecture. That is all I have for this module. Thank you.